Hi, Assalamualaikum warahmatullahi wabarakatuh. I am Shahriza Iskandar bin Muhammad Shah from Group 6. So today our group will be presented about COVID-19 cases in Malaysia from October 2020 until May 2022.
We choose the dataset of confirmed COVID-19 cases in Malaysia as the focus of this project. Using data spanning 20 months, we evaluated and compared the performance of several mathematical models, including linear, polynomial, and exponential functions to analyze the trend of infections over time. To determine the accuracy of each model, we calculated the sum of squares of error SSE, which measures how closely the predicted values align with the actual data. Based on these results, we then selected a suitable model to make predictions and forecast future trends in COVID-19 cases in Malaysia.
As you can see here, this is the datasets of confirmed COVID-19 cases in Malaysia from October 2020 until May 2022. So here, the x-axis we use is months or years, and for the y-axis we use the confirmed COVID-19 cases. Okay, as for the first question, which is least square of linear function, here we let the function as a naught plus a1 x. So the second one, we must find the normal equation, and by the REG mode in the calculator, we can find the n and the summation of x square, summation of y, and summation of xy. And from the REG mode, we can find the A0 and A1 by EQN mode in the calculator. So we will get the A0 is 32,404.1421. And for the A1, we will get 18,320.0150. So as we insert the A0 and A1 in the function, it will get the function equals to 32404.1421 plus 18320.0150x. So this is the graph for the linear function. Firstly, we plot all the points in a table in Microsoft Excel. Then we select all the data points and insert to create a graph, a point graph. Then as for the line, we insert the trend line, and we will get the equation same as we do manually just now. So we're moving to the next least square, which is polynomial functions. First, we let the degree of 2, so we will get m equals to 2, and the function equals to a0 plus a1x plus a2x square. And next we will find the normal equation, and by calculator, we will get the n, the summation of x, the summation of x square, the summation of x cubed, the summation of x to the power of 4, the summation of y, the summation of xy, and the summation of x square y. So after we insert all the value in the calculator, and by the EQN mode, we will get the a0 equals to negative 107,338.3228. For the a1, we will get 56431.5964, and for a2, we will get the negative 1814.8372, and we will insert all the value in the function as shown in the slide. So this is the graph for the polynomial function. It is same as before. We plot all the points in the Microsoft Excel, and then we create the graph by clicking the insert graph and select the point graph. So as for the line, we choose the trend line, and the function we will get as same as we do manually just now.
I will be presenting on linearization of an exponential function using regression analysis. We will transport exponential data into a linear form, calculate the regression, and derive the final model. We start with an exponential model of the form y equals to b times e raised to the power of ax. To linearize it, we take the natural logarithm of both sides, which is log y equals to log b times e raised to the power of ax. So the final equation is log b plus ax, where A not equals to long B and A1 equals to A. D shows the given values of X and the corresponding transform value of long Y. We have 20 data points in total by converting Y to long Y. We can now apply linear regression methods on a calculator to find A and B. So we will get N equals to 20. The summation of X is equal to 210. The summation of X squared is equal to 2,870. The summation of Y is equal to 237.034344. The summation of XY is equal to 1,559.7474. Solving the normal equation, we will get A not equals to 10.732. A1 is 0.1066. So sub into the linear model, long Y equals to 10.732 plus 0.1066x. Now we can revert back from the linear form to the exponential form. From A not equal to long B, we calculate the B. So we get the final answer is 45,820. And from A1 equals to A, we have A equals to 0.1066. So the final exponential function is Y equals to 45,820 times with e raised to the power of 0.1066x. Next, we can see the graphical representation of our exponent model. Y equals to 45,820 times with e raised to the power of 0.1066x. The blue dots represent the actual data point for long Y, and the dotted line is our regression curve, which model the exponential growth pattern. So I can observe that the curve follows the general trend of the data quite well. Most data points are closely aligned with the curve, indicating a good fit. Lastly, this validates our choice of using an exponential model for this dataset. In the end, this visualization confirms that our regression equation accurately model is underlying the data trend.
As we can see here, this is the dataset for linear functions, which is y is equal to a1x plus a0. And then we calculated the error of squares of each dataset by sum, and by sum of all error of squares, we got the sum of square errors, SSE. And for this linear function, the SSE is 706,597,206,000. The linear model provides a general upward trend but does not accurately capture the peaks and fluctuation in the data. The relatively high SSE confirms a poor fit. Next one is for polynomial function, y equal to a2x squared plus a1x plus a0. The SSE we got is 648,774,169,800. The quadratic polynomial captures the overall shape of the data much more effectively. It adjusts for sharp increases and decreases and offers a more accurate fit to the COVID-19 trend. It has the lowest SSE, indicating it is the best fitting model among all tested. And the last one we choose is exponential function, y equal to be to the power of ax. The SSE we got is 8476,269,56500. The exponential model assumes continuous growth, which overestimates value during declining periods in the dataset. This mismatch leads to the highest SSE, making it the worst fit among the models evaluated.
Based on the calculated sum of square error, we found that the least square polynomial function gives the best fit for predicting future trend. This is because it produced the lowest error compared to both the linear and the exponential model. So it is the most accurate model among the three. Now let's move to the prediction of future data. We use a quadratic function of the form fx equal to ax squared plus bx plus c. For our regression, the best fit quadratic equation is fx equals to negative a1814.8372x squared plus 5643.1.5964x minus 10733.3228. To predict the value when x equal to 20, we sub into the function and we will get the data is 219,359. So this confirms that polynomial model not only fit the existing data well, but it also relevant for forecasting future values. That's all. Thank you.